Hi, I'm Cassie, and I'm going to walk you through question 7 of the AAMC official physics question pack to help you prepare for the MCAT. The question is asking which waveform shown in the figure has the shortest period. Well, for those of you that just want a quick answer, the answer is going to be the third harmonic. Why? Well, as you increase harmonics, you increase the frequency of the wave, and that means you decrease the period. Because remember, period is the time it takes to go peak to peak to complete one wave cycle. Okay, so now if we do a more in-depth review of this question, we're going to review a lot of important concepts for the MCAT, like frequency and period of a wave, what harmonics are and how they relate to standing waves, and then how period and frequency of a wave changes as you increase harmonics, and finally, what resonance is. So let's jump right in with the discussion of what frequency and period of a wave, like a sound wave in this case, mean. So frequency is going to be how many cycles a wave completes per second. Now, our SI unit for frequency is going to be hertz. Remember that you should make an equation deck in Anki just for remembering what your SI units are for important MCAT quantities like frequency. So remember that we can visualize our waves as sine curves. So here our x-axis is time, and let's say we're looking at a 1 second period of time. So how many wave cycles here do we complete in 1 second? We complete one full wave cycle. So our frequency here is going to be 1 hertz, or 1 cycle per second. Now what's the period of a wave referred to? The period of the wave is going to be the time, in seconds of course, that it takes to complete one full wave cycle. So now period and frequency of a wave are going to be inverses of each other. So this equation here, t equals 1 over f, remember we tend to represent period as a capital T, whereas we represent frequency as a lowercase f, is an important one you need to know for the MCAT. So make sure you add it to your equation deck, along with the units of course, which are going to be seconds. So now let's think about why period and frequency are going to be inverses. Well, let's go ahead and draw another wave here. So what would be the frequency of this new wave? Well, how many cycles does it complete per second? We see that it completes 1 and then 2 whole cycles in a second. So our frequency here is going to be 2 hertz. Okay, now let's compare the period of these two waves. Our first wave, we saw that it only completed 1 whole cycle in 1 second. So our period here is going to be 1 second. Of course, we also could have found our period just by taking the inverse of our frequency. If we plug that in, we just get 1 divided by 1 cycle per second. Of course, if we take the inverse of our units, we're going to get 1 second per cycle. And then for the sake of simplicity, since we know we're just talking about 1 cycle, we drop our units of cycle and we just leave the seconds. So our period here would just be 1 second. Okay, now what's going to be our period of our second wave here? Well, we could do it just by looking at the graph and saying how many seconds does it take to complete 1 cycle. So if we look here, notice that we complete 1 cycle after only half a second has passed. So our period would be half a second. If this was more complicated, we could also plug this into our formula where we know period is 1 over frequency. And we'd get 1 divided by 2 cycles per second, which would ultimately just give us half a second. So the last important thing to note is don't get period confused with wavelength. Whereas the period of this first curve we have drawn here might be 1 second, the wavelength is going to be measured in meters. So let's say this is like 520 nanometers, for example. Okay, so takeaway, don't get period, which is in time, confused with wavelength, which is in meters. So far, we covered frequency and period of a wave. Now let's think about how frequency and period relates to the concepts of harmonics and standing waves. So the passage talks about the fact that we're talking about harmonics in the context of musical instruments. So to understand harmonics and standing waves, we're going to talk about the example of when you play guitar. So when you pluck a guitar string, what happens? You get a vibration, and that vibration essentially is the string moving up and moving down. So what we don't see with the naked eye is that vibration represents the fact that sound waves are getting sent along that guitar string. Remember we talked about in question 5 that sound waves are a type of mechanical wave. And mechanical waves, they have to move something, right? That's what mechanical energy is associated with movement. So in this case, sound waves, they are going to move or vibrate particles in whatever medium they're moving through. So in the case of a guitar string, they're going to vibrate particles in air, for example. And then depending on what frequency those vibrations are happening at, we hear that as pitch, the pitch of a musical note. And don't get that confused with tone, which is a little bit different. Tone has to do with the overall quality of the sound. So that includes things like frequency, but it also includes things like what kind of material you're using for the instrument, the type of string you're using, the thickness of the strings, and a bunch of other factors as well that contribute to the overall quality of the sound. Okay, so let's say I go ahead and pluck this guitar string. What's going to happen? I'm going to create a sound wave, and that sound wave is going to move along my guitar string. So let's just say it's going to move to the right, like this. Eventually, what's going to happen? It's going to reach the end of that string, the point where the string is attached to the guitar. We're going to draw that barrier point as a red dashed line here. And we know that when a wave hits something like this, it's going to bounce back. But it's not going to bounce back in the same way that it traveled to that barrier point. It's actually going to flip over and inverted travel backwards. So I can't draw this perfectly, but I'll link in the comments here a great animation showing how this happens. Let's say our reflected wave now is green. We're going to have a reflected wave that's traveling back, and notice that original wave and that reflected wave interfere with one another. And when that happens, we produce what's called a standing wave. So what is a standing wave? Well, here our original wave and our reflected waves are two traveling waves. Their maxima points, or their peaks, so that's like here and here and here, are always moving. So like the maxima of our original wave is always moving towards the right. Those peaks are moving towards the right, and the peaks of our reflected wave are going to be moving towards the left. So those are traveling waves. But when we get two traveling waves interact where they have the same amplitude, and that makes sense, they're essentially the same wave, just one is original, one's reflected, and the same frequency, and they're moving in opposite directions like this, they're going to interfere with one another in a way that creates a resultant standing wave that has peaks that don't move. Now, what's the simplest possible pattern that this could look like? Well, we just create a wave that only has one peak that doesn't move. So that might look like this. So this is our resultant wave in red dashed line here. This simplest possible standing wave pattern is going to be our first harmonic, which is also known as our fundamental frequency. The peaks of our first harmonic, which are going to be here and here, they don't move. Even though this resultant wave was produced by two traveling waves, which have peaks that move, the peaks of our standing wave don't move. And how are those peaks produced? Well, of course, it's going to be produced by constructive interference. We talked about in question 5 how constructive interference happens when two waves line up in a way where their amplitudes add together. So here, notice that our first harmonic has an amplitude that's much bigger. Remember, amplitude is that distance from the x-axis. That's much bigger than either of the waves alone. And that's because you're getting constructive interference between those waves happening, producing those peak points. Then, of course, what's happening over here and here, those are going to be our points of destructive interference, where our original traveling wave and our reflected traveling wave are interacting in such a way that they cancel each other out, so we get these minima points. So let's get down some terminology that's important to know for the MCAT for standing waves. Our peak points of our wave, so that's here and here, are going to be called antinodes. Our antinodes are places of maximum amplitude on our wave, so the max displacement of the wave. Now, the opposite of an antinode is going to be a node, and those nodes are going to be at the point where there's zero displacement of the wave. So for our fundamental frequency here, or our first harmonic, that's going to be only at the point where the strings are fixed to the guitar end, or right here and right here. Now, something special about our nodes, those are points of zero movement, just the stationary fixed part of the string. As we move up harmonics, we go to the second harmonic, the third harmonic, we're going to see that we add more nodes and antinodes. What do we notice here about how much of one wave cycle of our standing wave fits onto our string? Well, if this is the length of our string, which we'll call L, then we only have half a wave cycle that fits on it. So sometimes in the MCAT, you might see this equation come up, which is for a first harmonic or a fundamental frequency, that our wavelength is going to be equal to half of the length of our string, or 1/2 L. Now, there are other possible vibration patterns of how our original wave interferes with our reflected wave. As we go up harmonics, more of our wave cycle is going to fit onto the length of our string. So let's go ahead and take a look at what the second harmonic would look like. So our second harmonic here is going to fit a whole wave cycle onto the length of our string. So essentially that's going to look like this. Our wavelength is just equal to the length of our string. Now, notice that the frequency of the second harmonic is twice the frequency of the first harmonic. So if we designate that this is a 1 second period here for our first harmonic, then if we know our frequency is cycles per second, we do half a cycle in a second. So our frequency here would be 1/2 hertz. And then for our second harmonic, same deal. If this is 1 second and we fit a whole wave cycle, then our frequency is just going to be 1 hertz. And this trend is going to continue on as we go up harmonics. So let's go ahead and draw our third harmonic here. Here we see that we fit 1.5 wave cycles onto the length of our string. So we're going to get that our wavelength is equal to 3/2 of the length of our string. Our frequency, how many cycles per second do we have? Well, we have 1.5 cycles per second. So our frequency here is just going to be 1.5 hertz. Okay, so what do we notice about how our frequency changes as we increase harmonics? Well, we went from a frequency of 1/2 to a frequency of 1 hertz to a frequency of 1.5 hertz. So as we increase our harmonics, we're increasing our frequency here. And then we could go ahead and calculate our period for each one. But based off the fact that we learned before that period and frequency are inverses, if frequency is increasing as we increase harmonics, then period is decreasing as we increase harmonics. Or in other words, the time it takes to complete a cycle is decreasing as we increase harmonics. But if you want more practice on how to calculate period, you can go ahead and pause the video and I'll write the calculations out here so you can test yourself. Okay, so you should have gotten that your period for the first fundamental frequency here would be 2 seconds, for the second harmonic would be 1 second, and for the third harmonic would be 2/3 of a second. So there you see the trend where as we increase harmonics, our period is decreasing. So that's how we knew that the answer to this question was C, the third harmonic, because we know that the third harmonic must have the shortest period. Now, what do we notice about our nodes and antinodes as we increase harmonics? Well, let's take a look. So starting with our nodes, we said our nodes are fixed points, points where there's no movement. In our first fundamental frequency, the nodes are only going to be at the end of our guitar string. But as we go to our second harmonic, notice that we have a node in the middle as well. And that node in the middle, again, is a point of no movement. And then finally, as we go to our third harmonic, we get even more nodes. What about our antinodes, which remember are points of maximum amplitude or displacement of the wave? In our first harmonic, our fundamental frequency, we said our antinodes are just going to be right here. In our second harmonic, notice that we have more antinodes. It's as if our guitar string was almost split in half, right? As if you plucked the guitar string exactly in half, and each half of the guitar string was oscillating up and down instead of the entire guitar string, like in the first fundamental frequency. And then lastly, for our third harmonic, notice that we're going to have more antinodes still. So this would be almost as if you split that guitar string into thirds, and then each third was oscillating up and down on its own with a point of no movement in between them. Okay, so that wraps it up for understanding harmonics and standing waves and how they're related to period and frequency. Last up, we're just going to do a quick recap of what resonance is. Well, resonance is just a special type of vibration. It's the idea that when we disturb a medium at one of these harmonics, at one of its natural frequencies, so each of these harmonics are one of a medium's natural frequencies, then we produce a type of vibration that is going to be stronger. It's going to be of a greater amplitude than if we disturb that medium at a frequency that's not one of their natural harmonic frequencies. So like we saw in this example, if our first harmonic or our fundamental frequency naturally occurred at half a hertz, if you pluck a guitar string in a way that produces that kind of vibration, a half a hertz vibration, then you're going to get a tone, a quality of sound that is clearer, that is a stronger amplitude than you would if you had plucked that guitar string at a frequency that wasn't aligned with its fundamental frequency or one of its harmonics. So question to recap here, is all vibration resonance? No, resonance is a specific type of vibration where you end up in a signal that has a larger amplitude, but not all vibration is resonance. You can have vibration that's at a frequency that doesn't match a harmonic frequency, and then that would not be resonance. Okay, so that was a quick recap of what resonance is. Now let's do a quick recap of our key takeaways here that are going to help you prep for the MCAT. So to review, what's the difference between frequency and period? Frequency is how many cycles happen in a second. So in other words, how many wave cycles happen in 1 second. Our SI units to measure this are going to be hertz. Now compare that to period, which is not about how many cycles happen in a second. It's about how long a single cycle takes to happen. So the time in seconds it takes to complete 1 cycle. Then what's the relationship between frequency and period? They're inverses. So for example, period, capital T, is 1 over f, or 1 divided by frequency. So if you know the period of something, you can calculate its frequency and vice versa. You also know if the period of something is increasing, then its frequency is decreasing. We also touched on the fact that you don't want to confuse wavelength with period. So period is the time it takes for 1 cycle to complete. Wavelength is the length of that cycle. So wavelength you'll usually see on the MCAT measured in meters, specifically nanometers, because nanometers is used for the visible light spectrum. Then we talked about how harmonics are just specific frequencies at which material, like a guitar string, for example, would naturally vibrate. Now, every harmonic involves the formation of a standing wave. And remember that standing wave is just a result of 2 traveling waves that are traveling in opposite directions, but they have equal amplitude, interacting with each other and causing destructive and constructive interference. Remember that our points of constructive interference between our 2 traveling waves produce the antinodes on a resultant standing wave. And those antinodes are a point of maximum amplitude, versus our points of destructive interference, where the waves sort of cancel each other out, are going to produce our nodes, which are points of no motion on the wave. So those are either the fixed like ends, for example, of a guitar, or points in the middle where there's no motion for those waves. Now, how does period and frequency change as we increase harmonics, going from our fundamental frequency, which is also called our first harmonic, to our second and our third, and so on and so forth harmonic? Well, every harmonic after the first fundamental one is just going to be a multiple of that fundamental frequency. So if we say that that frequency is F, then the second harmonic has a frequency of 2F, and the third harmonic has a frequency of 3F, and so on and so forth. Now, whereas our frequency increases as we increase harmonics, since we know frequency and period are inverses, our period is going to decrease as we go up harmonics. And then lastly, we talked about how all of this relates to the concept of resonance. We said resonance is a type of vibration where you're vibrating something at one of its natural harmonic frequencies, so it produces a louder and clearer tone, a tone with a greater amplitude. So again, if you review questions really deeply like this, all the concepts that they're related to, then you're going to be ready to tackle whatever comes your way on the day of your MCAT. So I hope this helps. Feel free to drop questions and subscribe to my channel for more content like this.